You've probably heard about this, right? How easy it seems to be to trick AI models? Well, it turns out the answer to why this is so incredibly hard to stop, it's been hiding in a classic book from all the way back in 1979. We're going to dig into why prompt injection is this deep, fundamental, and maybe even unsolvable problem. And we'll do it through this amazing story about a music-loving crab and his record player, which is in for a really, really bad day.
So let's start here with this quote from Douglas Hofstadter's legendary book, Gödel, Escher, Bach. This is where we meet our main character, the crab. And this crab, he's just gotten his hands on what he believes is the perfect phonograph, a machine that can reproduce any sound flawlessly. Sound familiar? It's pretty much the exact same dream we have for AI today, isn't it? To build that perfect, do-anything, all-knowing system.
So yeah, the crab is absolutely positive he's got the ultimate sound system, a machine that can take anything you throw at it. And, this belief in perfection, that's the setup for a really clever and pretty destructive lesson. And then the tortoise shows up. He's the crab's very clever friend, and he's brought a gift, a custom-made record. But this is no ordinary piece of music. Oh no. This thing has been engineered with one purpose, and one purpose only: to completely destroy the very machine that tries to play it.
So get this, the title of the record is The Attack. When the so-called perfect phonograph tries to play it, the sound it makes, well, it produces the exact vibrations that will shake the machine to pieces. It's just a few notes, a little pop, and boom, the whole thing is just confetti.
So what's going on here? This trick the tortoise is using, it has a name. It's a really powerful idea from logic and computer science called diagonalization. The gist of it is this. If you build a system and claim it can handle any possible input, you can always, and I mean always, create one special input that talks about the system itself. And by doing that, you force it into a corner it just can't get out of. You make it contradict itself, and it crashes. Okay, so how did he pull this off? It's a four-step process, really. First, he gets his hands on the blueprints for the phonograph. He studies the system. Then, he analyzes those plans to find a fatal flaw, that one specific sound vibration that'll shatter it. Step 3, he records that exact sound. And for the final touch, he gives the record a title that points directly at its target. He's literally weaponizing the machine's own identity against it. It's brilliant, right?
And this is where it all clicks into place for us today. The perfect phonograph? That's our general-purpose large language model. The record designed to break it? Well, that's a prompt injection attack. And that fatal vibration? That's just a vulnerability somewhere in the AI's code or its rules. The parallel is just perfect.
But the story doesn't end there. The crab isn't one to give up. He goes right back to the drawing board and builds something way, way more sophisticated. He calls it Record Player Omega. And this thing isn't just a record player anymore. It's a full-on defense system designed to see threats coming and neutralize them before they can do any damage.
And what's just wild is how Omega's defenses from this 1979 book are basically a blueprint for modern AI safety. Seriously, it scans the input first, then it predicts what will happen by running a safe simulation, and then it actually rebuilds parts of itself to handle the threat. This is exactly what we try to do today. Pre-execution analysis, simulating tool calls, dynamic reconfiguration, it's all there. This is state-of-the-art AI security dreamed up decades ago.
So you got to be thinking, okay, this has to be it, right? Is Record Player Omega finally the perfect, unbreakable machine? Well, as Hofstadter shows us, the answer is a big, fat no. Even this super clever, self-modifying system has a weak spot.
Think about it. No matter how much the system changes and reconfigures itself, there's one piece that has to stay the same, right? The part that's doing the reconfiguring, the core control unit. So what does the tortoise do? He just makes a new record designed to attack that part. There is always an Achilles heel.
And this gets us to the core dilemma, the big trade-off in AI. You've got your high-fidelity systems, the really powerful ones that can run code, use tools, access the internet, they're amazing. But they also have a massive attack surface. On the other hand, you have low-fidelity systems. They're way safer, but they're also, well, kind of useless. You can't get rid of the risk. You can only decide where you want to put it. So this whole experience, it completely changes the crab's perspective. He has this big realization. Perfection is impossible. It's a fool's errand. So he just gives up on that goal. And instead, he starts focusing on something way more practical. Just survival.
His new aim isn't to be a universal player that can handle anything. Nope. The goal now is simply to not get destroyed. And if that means it can only play a small, trusted list of songs, so be it. And that shift, right there, from trying to be universal to trying to just be a survivor, that is the absolute core of how we think about building resilient AI systems today.
So what does his new strategy look like? It's basically two parts. First, he cares about provenance. Where did this record come from? He uses secret labels to verify it's from a trusted source. And second, he uses allow listing. He'll only play records that have that trusted label and that fit his pre-approved musical style. It's all about limiting what the system is even allowed to do, just to keep it safe.
Okay, but here's the next twist, and it's captured perfectly by that famous painting by Magritte. This is not a pipe. A picture of a pipe isn't a pipe. A label on a box isn't the same as what's in the box. And this is the problem. Instructions can be hidden in plain sight, disguised as something totally harmless.
And yep, you guessed it, this is exactly how the most devious modern attacks work. Malicious instructions get hidden in places you would never, ever think to look. The alt text for an image, an SVG image path, a document file name, even weird Unicode characters. Benign data, stuff that's supposed to be helpful, like text that you pull from a database in a RAG system, can suddenly become a weapon.
Okay, so let's recap. We've accepted that a perfect, unbreakable system is just not going to happen. So what does a real-world, practical playbook for a survivor look like? How do you actually build resilient AI?
Well, it looks like this. It's all about layers of defense. First, triage. You classify the risk of an input and you track where it came from. Then, normalize. You sanitize the input, strip out anything that looks dangerous. Next up, plan. You decide ahead of time what the absolute minimum privileges the system needs are. Then you simulate. You do a dry run of any actions in a safe sandbox. Then and only then do you execute, and you do it with guards like timeouts and rate limits. And finally, you have to be able to detect and recover, spot when things go wrong, and be able to shut it down. See, it's not about being invincible, it's about being tough and resilient.
Now, if you're in security, you might be thinking, hey, this sounds a lot like SQL injection. And yeah, it's a good starting point, but the comparison breaks down really fast. See, with SQL injection, you're dealing with a bounded language. SQL has a fixed grammar, there's a finite list of bad things you can do. But with prompt injection, you're dealing with natural language, which is pretty much infinite. A SQL database only understands SQL. An LLM understands language itself, and you can instruct it to mess with files, APIs, the command line, anything it's hooked up to. The attack surface is just monstrously bigger.
And this quote from the book just nails it. It really gets to the heart of the whole issue. The problem, the real defect, might not be in the AI models themselves. Maybe the defect is in us, in our crazy expectation that we can build something that is both all-powerful and perfectly safe. We just can't.
So, how does the story end? It ends with this incredibly powerful, fragile image. A beautiful glass goblet just shatters out of nowhere. And then, dead silence. It's this perfect metaphor. It's a reminder that fragility isn't some bug we can patch out of complex systems. It's a feature. It's baked right in.
And so that leaves us with this one big question to chew on. If a perfect, unbreakable system is impossible, if it's completely off the table, then what should we be doing? The real work, it seems, isn't about engineering an unbreakable machine. It's about engineering our relationship with AI. So, what does a healthy, resilient relationship with these powerful but forever fragile technologies actually look like? That, right there, is the challenge for all of us.